Today we're going to talk about motion maps and velocity versus time graphs for both objects moving at a constant velocity as well as objects accelerating. We are going to use some specific colors to represent some things. We're going to use the color black to represent position. We're going to use the color blue to represent velocity. And we're going to use the color red, to represent acceleration. When something does accelerate. For this first problem here, it asked us to draw a motion map and a velocity versus time graph for an object that is moving in a positive direction at a constant velocity. Now they don't tell us exactly what the starting position is, but if it's going to move in a positive direction, it's going to benefit us to start somewhere near a clock reading of 0, or a position of 0, excuse me. So if this is moving in a positive direction at a constant velocity, since it's a constant velocity, the position dots are going to have to be equally spread out. If it's a constant positive velocity, positive means that the velocity vectors are going to have to be in a positive direction, right? And they'll all have to be the same length. To make sure that I tell other people that these velocity vectors are all supposed to be the same length, I'm going to mark each one with a hash mark, a positive constant velocity. How would that show up on a velocity versus time graph? Well, because it's a positive velocity, we're going to want to make it above the time axis. And because it's constant velocity, it would be a horizontal line. Notice that there are no numbers on our velocity versus time graph or on our motion map besides the number 0. So these are considered qualitative motion maps and velocity versus time graphs. Let's take a look at number 2. On number 2, again, the object is moving in a positive direction, but now it's speeding up. So if we start with a position of 0, if it's speeding up, will the position dots start close together and get further apart, or start far apart and get closer together? In number 1, or in letter A, the positions of the dots were equally spread out, but in this case, if it's speeding up, we'd have bigger and bigger changes of position per unit time. And the velocity vectors would be getting longer. Should I put hash marks on these velocity vectors? And the answer to that is no, because they're not all the same length, because the velocity is increasing as time goes on. What about the very first position dot? Does it get a velocity vector or not? Well, the question is it moving at time 0? Now, this problem does not specify was the object at rest or not. So we could draw it more than one way. But if we were to assume that the initial velocity is 0 and we had a positive increase in velocity, then the very first dot would have no velocity if we assume that the velocity is 0 at time 0. What about the acceleration? Well, in this case, we know that the acceleration versus time graph might look something like this. Since we have a positive constant slope, that means we have a positive constant acceleration. The slope of a velocity versus time graph tells us the acceleration, which means for our acceleration versus time graph, it would be a positive constant acceleration. Positive, it's above the time axis, and constant, it's a horizontal line. So how might that show up on a motion map? Well, it would mean that in addition to the object at this first second clock reading, it has a velocity, but it also is accelerating. But because the acceleration is constant, we're going to have to add hash marks to these. Constant positive acceleration. And that simply tells us how much the velocity vectors are increasing per unit time. But again, let's consider what happens at time 0. At time 0, is it accelerating? To do that, we can consider two things. We could consider the y-intercept of our acceleration versus time graph. Is the y-intercept 0? It's not. We've got a positive acceleration, so we've got some acceleration at time 0. The other thing we should do is consider what acceleration means. Acceleration always describes how velocity is changing. At time 0, the velocity is 0, but some moment later, it's moving. For that to have happened, the velocity must be changing. So we do need to have an acceleration vector at time 0 as well. And again, these red acceleration vectors should all be the same length. Let's take a look at letter C. In this case, we're moving in a negative direction at a constant velocity. If we're moving in a negative direction, should we start close to 0 or far away from 0? That's right, we should start far away from 0. If it's at a constant velocity, should the position dots be getting closer together or further apart or equally spread out? They should be equally spread out. I'm just using my fingers to measure these. You could pull out a ruler or use a portion of your pencil or whatever works for you. Because this is a constant negative velocity, our velocity vectors are going to be in a negative direction, all right? And I could actually cheat on this one. Oops, maybe I can't. I might be able to cheat and see if we can use my infinite cloner button and actually make all of my velocity vectors exactly the same length. And notice that the velocity vectors don't need to run exactly into the next position dot, which I didn't do a great job of here. They're kind of running into the next dot, but that's not required. So what would our velocity versus time graph look like? Well, just like before, it's a constant velocity. But is it a positive velocity? Nope, it's moving in a negative direction. So we're going to have to take that line, and it's a constant negative velocity. Well, I don't know how to erase that. Let's see how to do that. I'm not sure. We'll fix as we go. So it's a constant negative velocity. What about if an object moved in a positive direction while slowing down? Well, if it was slowing down, that would mean it was moving really fast at the beginning. So we would expect a big change of position at the beginning, and as time goes on, the distance between those position dots would get smaller and smaller. At the beginning, it would have had a big positive velocity, and then a smaller positive velocity, and a still smaller positive velocity, and then smaller, and that last position dot, if we assume that it slowed down to a stop, the last dot would have no velocity vector at all. What would the velocity vector look like for this one? Or excuse me, the velocity versus time graph. Well, if we assume that at the beginning there was a big positive velocity, where would that be? Well, this is a big positive velocity, and at some time later the velocity was 0. So if it starts with a big positive velocity and the velocity, you have a smaller positive velocity at like the second, and it comes to a stop, our velocity vector, velocity versus time graph would look like this. That makes me think, what would our acceleration versus time graph look like? If this has a constant negative slope, that means we have a constant negative acceleration. So constant acceleration means we have a horizontal line, but if it's a negative acceleration, it's going to have to be below the time axis. At all times, the acceleration was negative. So that means even though at time 0 we had a big positive velocity, the velocity is changing in a negative way. So a little while later, the velocity is a smaller positive velocity. A little while later, a smaller positive velocity, and so on. But what about this last position dot? We know that it doesn't have a velocity vector because we said that it would slow to a stop. However, does it get an acceleration vector? Well, let's go back to our acceleration versus time graph. Is it accelerating at time 0? And the answer is yes. How can you defend that by the motion? Well, if it was not moving at the very final clock reading, immediately before the final clock reading it was moving. For that to happen, the velocity had to have changed, which means it had to have had a change in velocity, which is an acceleration. Again, these acceleration vectors should all be the same length. I didn't do a very good job making them all the same length. That was no good. Let's see if I can do a better job making them all the same length. this is a little bit better. Let's take a look at letter E. An object moved in a negative direction while speeding up. If it moved in a negative direction, we're going to want to start way in a big positive position so that we can move towards 0. And if it's speeding up, we're going to have to start with our position dots close together. And as time goes on, the distance between our position dots gets further and further. If we assume that it starts at rest, the first dot would not get a velocity vector, and then we get longer and longer velocity vectors, no hash marks. What would the velocity versus time graph look like in this case? Well, it's a bigger and bigger negative velocity. And if we assume that at time 0, the velocity is 0, that would be here. These are positive velocities, these are negative. So the initial velocity is 0 and a bigger and bigger negative velocity. So it would look like this. Would there be acceleration vectors? What would the acceleration versus time graph look like for this one? Since we have a constant negative slope, that means we have a constant negative acceleration, which means our acceleration versus time graph would look like this, and therefore we need to have constant negative acceleration vectors that would look like this. Again, I'm going to cheat and use my infinite cloner button to make sure all my acceleration vectors are the same size, and again, all that does is reinforce how much the velocity is changing in a negative direction. Let's take a look at the last problem. After an object moved in a negative direction for a while, slowing down, then it remained stopped. So it's going to move in a negative direction while slowing down and then remain stopped. Well, if it's slowing down, that means it's going to have to be going fast at the beginning and then slower. The distance between the position dots will have to get closer. But then it remains stopped. Do you remember what the position dots look like if something remains stopped? And the answer is they stack. We're representing, remember, this is a position line, right? They're at the same position, a clock reading later and later and later. So initially we've got a big negative velocity, and then a smaller negative velocity, and a smaller negative velocity, and a really small negative velocity, and then stopped. And what about our acceleration vectors? Well, let's consider what would the velocity versus time graph. We know we start with a big negative velocity, and at some time later the velocity has to be 0. So it looks like our graph, our velocity versus time graph is going to look like this for phase 1, and this for phase 2, suggesting there is no velocity during the second phase. What about our acceleration vectors? Well, if you consider what our acceleration versus time graph would look like for this, at the beginning of this, so for this section here, the slope is tilted upward, which means it's a positive slope. So we have a constant positive slope, which is a constant positive acceleration for phase 1, which would look like this. But for phase 2, the slope is 0. So we would have to say that for phase 2, the acceleration is 0. So we have two horizontal lines. One is a positive constant acceleration, one is an acceleration of 0. So we add our acceleration vectors, a constant positive acceleration, so it's going in a positive direction, put hash marks on those, suggesting they're at the same length. And even that first stopped dot will get an acceleration vector, but none of the ones after that. Why don't the position dots afterwards get acceleration vectors? Well, because the velocity is not changing. No change in velocity, no acceleration. I hope this helps you better understand motion maps for uniformly accelerating objects and an introduction to using both velocity and acceleration vectors on the same motion map.